Okay, in this video I want to talk briefly through or maybe not so briefly, but go run through the second lab and show you a little bit how to do this in R. If you have not done the lab yet, have not finished all the questions in the lab yet, I would strongly urge you not to watch this video. Yeah, so you should really try to figure this out for yourself first, and then watch the video to help you out. And even if you get stuck, you really want to Google things first. If you want to run a regression and you forget how to do it, just Google running a regression in R and see what comes up, and try that way first. Because really it is in practice. But I'm also very aware that there has been a little bit of a lack of time in the previous semester to do everything, and I want you to be up to scratch, so I want to talk you through this. Now, first I'm going to say that I can type all my commands here. I can type import, I can do library, Rio, or something. I can do everything here. But whatever I do here in the console will then be disappearing again, and I need to keep track of everything I do. So always make sure you make a separate R file. This can be an R script or an R markdown file, whichever you prefer. But that way you keep everything together. Today I will do an R script, but actually for myself, most of the time I work in Markdown. I might show you in a video later. So here, this is just R code. We can type any command. With a hash command, we can add comments. So I will add a little bit to show what I'm doing. So it is lab 2 already. And I have on the video on the side, you can also see that I have the PDF open. Sometimes I need this to, I hope I can copy paste. That's not going to work here. I just type it in. It's not a big deal. So we start. First, we just need to get the films data set. We need to get that opened. So we need the Rio library. If you don't have the Rio library, if you get an error message right away, you probably need to go to install packages, Rio, and then see whether this works. This is one of the few commands you would actually put in the console rather than in the script. And the reason is that you would install this only once, and after that it's on your computer. You don't need to anymore. Here on the top should be all the commands you are going to regularly use. So whenever you need to retry something, you will need to get back to the top screen, the script screen. But at the bottom in the console, there you do the commands that you only need once. I don't need this. I have the Rio library, so I'm not going to bother. And then this is already on the slide, so you can copy this directly from the web. So import can open almost any type of data file. And in this case, we have something in a rather lengthy URL, unfortunately. So DTA means it's a data file, but import can see that as well and can then open it, no problems. Here on the right, I tend to have the environment tab open. There's also history, connections, help, environment. I tend to have environment open, so I can see what objects are in my system at the moment. I would recommend to not save that normally and not keep from previous sessions all kinds of objects there, so it's always empty. There's this broom here that you can empty it, and here's the films object. And if I click on that, I can see a little bit what the variables are. So there's a title variable, a year, length, cast size, rating, desk length. I can also click on films, and it will open it as a data set. It's a bit easier to see. That I tend not to have open, but maybe I'll leave that now. Okay, at this stage I should probably save what I have. Yeah? I go to File, Save, and give it some name. Do that quickly. Yeah, so I can just press Save, because that will otherwise come up automatically. And so the first thing that the assignment asks is to recode this variable rating so that we have a binary variable, a variable with just two categories. And there I would actually use a different library. Personally, I would use the dplyr library. And the dplyr library has nice tools for managing data sets, for selecting, renaming, mutating variables, and so forth. And one of the features it has is a pipe command. The pipe command looks like this. It means take the output on the left and make it the input of the function on the right. And that means you can chain a lot of commands right after each other. So here I will use the films dataset as input, and on this dataset I want to use the mutate function, which is a function that is there to change or add new variables. And I'm going to add a new variable. What do they call it? High rating, I think. High rating. And then there's different ways we can do this. So to test whether the rating is higher or equal to than 3, you do something like this. This will measure whether the rating is higher or equal than 3. But that means that we now have a true or false variable, and it's at 1 or 0. One thing I can do is to make it an integer, and that will turn the trues into 1 and the false into 0. An alternative is to do films mutate high rating, because if else so if else is a command that takes as the first parameter some comparison, and then as the second parameter whatever should be the result for the true cases, and the second whatever should be the result for the false cases. So here we want everywhere where this is true we want 1, everywhere where this is false we want 0. So in total this does the exact same thing as this. Now finally I have changed the films dataset here, but I need to make sure that I then also save it again. So I will just save it as films, and that of course also needs to be done here. So I can run this line and I can look at the data sets, and there's now a high rating. And indeed when the rating is a bit higher, this is a 1 now. Yeah? So we have that step done. Let's go back to the assignment. Regress test length on a constant. Now normally a regression looks like this. We have the linear model, LM, then the dependent variable, and then a tilde, and then all the independent variables. Now the only exception is when you want only the constant, then you have to put a 1 here. And then we can specify the data set. So this 1 here, you don't normally have to include that. That's the intercept. You don't include that when you only when you already have other variables as well. The intercept is assumed to be there. But if you don't have other independent variables, you need to make it explicit. So that will work. That will give you this output. But this is not the most easy to read. I would normally put maybe something like summary. That will give me a better table, a more interpretable table. Yeah, so here you have the coefficients. This is the coefficient estimate, beta hat. This is the standard error, the square root of the diagonal of the variance-covariance matrix. This is the t-score, which is just this divided by this. And then this is the p-value associated with such a high t-score. And this 2 to the power e minus 16 means 0.00 and then 15 zeros, and then comes the 2. Yeah, so that should be read as 2 to the power 2 times 10 to the power of minus 16. Yeah, so that is okay. Yeah, that's not helpful. But so that is how you read that. So that means that it is a tiny number. 10 to the minus 16 is 0.0000, 15 zeros and a 1, and then multiply to the 2. In other words, this just means very, very, very small, highly significant. Okay. That just means that the length of the description in this movie guide is normally never 0, but yeah, that's obvious. The second regression, description length on cast size. So we get a similar kind of table. You can see that the intercept is automatically there. We did not have to include it manually. And we get the beta coefficient for the intercept and the standard error, the square root of the diagonal of the variance-covariance matrix. Again, a very low, but a lot higher than what we had before, with very low p-value. And we also get a coefficient for cast size with a standard error, t-value, and again, this is 0.0000125. Yeah, so you move the dot 5 points to the left. That is what this means. So you get 0.0000125. That is lower than 0.05, and so we get stars. And this means that if for every one additional cast member in this movie, the length of the movie description will be about 60% of a sentence longer. Yeah? I think this desk length is in sentences. Yeah, it's the length of the description. So you get about half a line more in this guide, or 60% more, 60% of a line more, if you have one more cast member. What is the next question? Regress description length on cast size, high rating, and length. Yeah, so I'm going to copy this, plus high rating, plus length. So length is the length of the movie, yeah? Not the description, but the movie. So we see that if a movie has a high rating, that does not have a significant effect. So the description tends to be longer, about 0.6 of a line longer, if it has a high rating, but there's a high standard error. So there's great uncertainty around this correlation. It means that if we take different samples, we might very well get very different results. So our p-value is quite high. Yeah, so if we were to reject the null, that there is no relation between the rating and the length of the description, we have a 30% chance almost that we are wrong in rejecting the null. So that is high. The description is still about half a sentence longer for every new cast member, and this is still highly significant. And also if the movie is longer, you get a significantly longer description. Now I forget how the length is measured. I think it is in minutes. See on the top right you can see it's 89, 127, 128, so that's like 1.5, 2 hours. So that is in minutes. So every minute longer that the movie is, you get about 4% of a sentence more in the description. Yeah. So if you have so what is that times an hour? Yeah, so if you have an hour more, you get 2.5 sentences more. So there's a real correlation between the length of the movie and the description length in the guide. Now we're going to continue looking in question 2. We continue to look at, so this is question 1. In question 2, we continue to look at that last regression, so where we have the full model, but it is asking to look at some of the results. So I'm going to save this result. So here I'm going to insert some name, maybe model, I don't know, whatever you want to use, MDL. Yeah, so I'm going to assign that. So even though we do the summary and we run the regression, we also save this. If I now run this command, I can type model and I can see the results. I have it saved. So then I can look at, for example, the residuals. Yeah, residuals of the model. There are the residuals. Yeah? So we have 100 observations in this data set. It's 100 observations and 7 variables. And so we also get 100 residuals. Yeah? And that's where they are. Yeah, which observation has the largest? So let's see if we can sort this. That works. And so the largest one is here, is the 41st. Is that how you say it? The 41st observation has a residual of 9.3, and that is by far the highest. Yeah, so that's it's observation 41. Yeah. Compute the mean and the median of the residuals. So there is no missing cases here, so that makes it easier. If there was, you would have to add something like this to make it work. Yeah, but we don't have to do that now. But you would have to do that if there are missing cases. And you can see that the mean is practically 0, right? So this means move the decimal points 17 points to the left. So it is 0.0000 up 16 times, and then 7, 8. And that makes sense because for regression analysis, by definition, the mean of the residuals is 0. Yeah, so actually 0 by definition. And so the only reason it is not 0 and it's approximately 0 is because computers can never be as precise as mathematics, pure mathematics. Right? So that is just computer inaccuracy. I add this NARM is true, so like ignore missing data because it's good to make that a habit. You really don't need it now. And we have the median. So about 50% observation. So it's not entirely symmetric. It should actually be symmetric, but it's clearly not. Right? So the median, 50% more observations are below 0 than above 0. So it's a slightly skewed distribution. No, it does not ask for a histogram, I guess. But I would like to see that now. So I'm going to do that. So that was not asked for in the assignment, but just to have a quick look. That's not enough breaks. So yeah, you can see that there are a few outliers there on the right, a few very high residuals, but a lot are sort of around -2. So it's a really skewed distribution. And that is probably because the original variable was not particularly normally distributed. This dollar, so this is the data films and then the variable guest length. And that also has a bit of a skew, yeah, because there's a few films that have a particularly long description. So in that skew, so that also then translates into skew in the residuals. Okay, neither here nor there, but that's why the mean and the median differ. That means there's a skewed relationship. Compute the correlation between the residuals and the fitted values. So we have the residuals, they are here. We also have the fitted values, so that's the predicted values. Yeah. So we get 100 predictions of the lengths given cast size, high rating, and the length of the movie. And we can look at the correlation. So the correlation between the residuals and the fitted values, yeah, is 0.0000308. Very, very low. Practically no correlation. Yeah, that's good. Computer correlations between the residuals and lengths. We can do that. Films length. Again, practically 0. That's good. What will be the difference in predicted description length between high and low rated movies? That is actually quite straightforward. We can just go back to the coefficients. I'm not sure why that is asked now and not earlier then. Yeah, but this is the rating, so that is a difference of 60%, 63% of the sentence. So high rated movies have about 60% more in terms of the length of the description, but it's not statistically significant. Okay, so that is all with for the film's data. Let's go to question 3. Maybe I should put this here. Okay. So US is importers. Website again. Sorry for the long URLs. We do are just copy and pasting anyway, as we should. That works. So we have a new data set here. So you can see the model here on the right. You can see the US data set, 2,000 observations, much bigger data set, 10 variables. And it has some variables on individuals. Okay. Regress weights on education, experience, and race. Yeah? So summary, ln, wage, education, plus experience, plus race. Yep. Data equals. So here we have everything is highly significant. It's more easy to be significant. We discussed this in the power of tests and the video. When you have more observations. So everything is statistically significant. And the more educated, the higher your wages. The more experience you have, the higher your wages. And race leads to a negative wage. But we don't know exactly how that is coded. There we have it. So description of the data is there. So it's the same link as the link here, right? Exactly the same, except instead of DTA, it's TXT. And then we see that 1 means black and 0 means white. Yeah? And other races are not in the sample. Experience is years of experience, education is years of education, and wage is the weekly wage in dollars. So if you have a year more education, you get $50 more per week in salary. If you have 1 year more experience, you get nearly $10 more. And if you are black, you get $125 less than if you are white. Yeah? So that's the result of this data set. And that was the interpretation. Plot the residuals against fitted values. Okay, so we can do that. The easiest is this. Residuals of the model. So I need to save it again. The residuals of the model against fitted values of the model. And that's really all we need to do. And we get a plot here. I'll make this a bit bigger. You can't properly see this on the video because of the other file that's in front of it, but it gives you some idea. One thing that you will notice here is that on the left it looks very different from on the right. So there's a clear correlation between the amount of variance in the residuals and the value of the of y hat. Yeah? So on the x-axis here is y hat, the fitted value. The fitted value is the predicted value of y. On the y-axis is the residuals, E in the slides. Yeah. So, right, I could have add those labels actually if that helps. So this is y hat, and this is E. Yeah. And then you can see that the variation in the residuals in E is much higher when y hat is high and much lower than when y hat is low. And similarly, it asks for to look at the education variable. So then we don't have y hat, but we have education. And again, you will see that for lower levels of education, the variance is much lower than for higher levels of education. That really violates this heteroscedasticity. So the conclusion is high levels of heteroscedasticity, which is what we're going to talk about later. Yeah, but it means, i.e. the variance of residuals E vary depending on y hat or x. Now we assume it's constant when we calculate standard errors. Yeah, so that is a problem. Yeah, so this that we assume that we saw in the lecture today, and this we can see in the plots here. And this is a term that will be clarified that will be in next week's material. And now you can repeat everything by putting log around wages. Yeah? So repeating everything is done by copy pasting. Log wage. Yeah, this will have different results, different numbers, but the plots will also look different. This looks like a very random cloud. This looks like a very, still a problem. Yeah, plot with fitted values much better. Still problematic. But I'm not so sure actually. So the main variation is just also the amount of data. So it's not too bad. And then finally, question 4. Rates on education, rate, experience, and data. Okay, that is a little bit funny. That is a bit of a copy. So what proportion of the variance is explained, and you can actually just see that right away by looking at R squared. Oh, sorry, that is for the log. So we look at this again, R squared. Yeah? Yeah, so 14% of the variation in the dependent variable in weights is explained by looking at these three variables. When you don't log weights, when you log it goes up considerably to well, no, it goes up to 18%, still low. Yeah, so it's a pretty, the model does not explain all that much. Okay, I will stop there. This gives you a good idea of how to look at the data. To just quickly go over a few things again, library Rio is for the import command to open the data sets. Library dplyr is for the piping command that we have here, and also for a lot of functions for manipulation, such as mutate or select and so forth. Summary and lm together helps you to run a regression. Dependent variable first, independent variables on the right hand side, and then you specify the data set. And you can also save it under a name if you later want to access it again. For example, to get the residuals, predicted values, and so forth. The plot command to make very simple scatter plots, but most of the time when we use plots, we use a different library. But this is the built-in library, and it's easy enough for these quick plots that we want here. Okay, I'm going to stop there.